What if I told you we have built machines that can map something we cannot see, cannot touch, and cannot directly photograph? Not stars, not gas, not planets. I am talking about dark matter, the invisible scaffolding of the universe. And the reason this is suddenly possible is not because dark matter has become easier to detect. It is because our telescopes have become better, our simulations have become deeper, and AI has become good enough to pull structure out of noise that used to overwhelm every classical method. Dark matter and dark energy make up the overwhelming majority of the universe, and in a typical galaxy, the missing mass is about 10 times larger than the mass in visible stars. Dark matter itself does not emit light. Astronomers infer it indirectly from gravity, including gravitational lensing. So tonight, we are not asking whether dark matter exists. We are asking a much more interesting question. How do you reconstruct an invisible cosmic web from tiny distortions in galaxy shapes? And why is AI becoming the best tool we have for that job? The answer starts with weak gravitational lensing, the main technique used to map dark matter at large scales. Here's the basic idea. Light from a distant galaxy travels toward us through a universe filled with matter, normal matter and dark matter alike. General relativity says that mass bends space-time, and light follows that curved geometry. The result is weak gravitational lensing, a tiny, coherent stretching and shearing of background galaxy images by foreground mass inhomogeneities along the line of sight. On its own, one galaxy looks almost random because galaxies have many intrinsic shapes. But if you average over millions of galaxies, the subtle pattern of distortion begins to reveal the hidden mass distribution that caused it. That is why weak lensing is so powerful. It does not depend on dark matter emitting light, forming atoms, or producing radiation. It only depends on gravity. NASA's Roman Space Telescope explains that weak lensing measurements will reveal clumps of dark matter by tracking distortions that are far too subtle to see in any single galaxy, using the shapes of hundreds of millions of galaxies. Roman's goal is to map both normal and dark matter across a huge span of cosmic history, from shortly after the Big Bang to today. Euclid is built for the same mission from a different angle. ESA says Euclid will map the geometry of the dark universe by measuring galaxy shapes and redshifts out to about redshift 2, corresponding to roughly 10 billion years of look-back time, and it is designed to cover more than a third of the sky. ESA also states that Euclid's weak lensing program is intended to produce high-resolution 3D dark matter maps over the sky, and to investigate the nature and distribution of dark matter itself. Now, for the catch, weak lensing is not a clean image of dark matter. It is an inverse problem. We do not observe the convergence field directly. That is the map of the projected mass density we actually want. Instead, we observe galaxy shears, noisy, distorted shapes, and then we try to reconstruct the mass map from that. In the literature, this reconstruction is described as ill-posed because galaxy shape noise, missing data, and observational artifacts such as bright stars, cosmic rays, and CCD defects all break the problem apart. Different reconstruction methods can therefore produce different maps from the same data. This is also why traditional methods start to struggle on small scales. On large scales, the matter field is close enough to Gaussian that the two-point correlation function, or equivalently the power spectrum, captures a lot of the useful information. But on small scales, nonlinear gravitational collapse creates a highly non-Gaussian field, and the two-point function leaves a large amount of information behind. That is exactly the regime where future surveys like Euclid, Rubin, and Roman become most valuable, because they reach the angular resolution and depth where those nonlinear structures start to matter. That is the technical reason AI enters the story. AI is not replacing gravity, it is replacing fragile compression rules. Instead of forcing the universe into a statistic that may throw away useful structure, machine learning models can learn directly from simulated weak lensing maps how the underlying cosmology and mass distribution are encoded in the full pattern of shear, peaks, voids, and higher-order features. A recent benchmark paper on weak lensing machine learning says the field now needs methods that can handle uncertainty, systematic effects, and distribution shifts because real observations and simulations never match perfectly. The simplest way to think about AI and dark matter mapping is this. We feed it thousands or millions of simulated universes, each with known cosmological parameters, and we ask it to learn the forward relationship between mass and the observed weak lensing signal. Once trained, the model can infer the hidden parameters or reconstruct the mass map from real noisy observations. The key idea is simulation-based inference. Learn the posterior distribution directly from data rather than relying only on a hand-built analytic likelihood. A 2024 benchmark on weak lensing cosmology explicitly describes this shift, noting that log-normal forward models can generate LSST-like convergence maps, and that nonlinear structure makes the field highly non-Gaussian, so richer inference tools are needed. That is where convolutional neural networks come in. CNNs are a natural fit because weak lensing convergence maps look like images. In a 2024 study on weak lensing cosmology, CNN-based methods achieved about 5 times stronger constraints than the power spectrum on mock data without baryons, about 3 times stronger than peak counts, and about 2.3 times stronger than the power spectrum when baryonic physics was included. That matters because baryons, gas, stars, feedback from galaxies, and AGN can alter small-scale structure and complicate the mapping from dark matter to lensing signal. So the AI is not just detecting a prettier pattern, it is extracting information that classical statistics often fail to preserve. In practice, these models are trained on mock weak lensing maps that include realistic survey noise and then tested on cosmological parameters like matter density, omega m, and clustering amplitude, sigma 8. The appeal is not magic. It is dimensionality reduction with a learned prior. A CNN can combine local features, tiny peaks, ridges, void boundaries, and filamentary texture across the full map in a way that is hard to encode with simple peak counting or the power spectrum alone. And because the late-time density field is non-Gaussian, those higher-order features carry genuine cosmological information. One of the strongest uses of AI in dark matter mapping is denoising. Weak lensing observations are dominated by shape noise, which comes from the fact that galaxies do not all have the same intrinsic orientation and ellipticity. That noise hides the small-scale structures where the richest information lives. A 2025 diffusion model study on weak lensing mass maps explicitly says that removing shape noise lets us access information at small scales where the noise otherwise dominates. The authors trained both a GAN and a diffusion model on tens of thousands of mock observations and found that the diffusion model outperformed the GAN on almost all tested statistics, reproducing the correct small-scale structure more effectively. That's a big technical step because denoising weak lensing is not just smoothing an image. Over-smoothing destroys the very peaks and filaments that trace the mass distribution. Good denoising has to reduce noise while preserving the power spectrum and the non-Gaussian statistics, things like the bispectrum, peak counts, minima counts, and the one-point probability distribution. The diffusion paper reported that its model could recover these statistics down to small scales and reconstruct high-resolution mass maps with sub-arc-minute fidelity. That is important because the universe's dark matter web is not just diffuse haze, It is a structured network of filaments, voids, and halos. A newer diffusion-based reconstruction paper pushes the idea even further. It treats the mass map problem as an inverse problem solved with diffusion posterior sampling, using a diffusion model as a prior and then conditioning it on noisy shear data. The authors show that the standard DPS method can produce biased inference, and they correct that bias by downweighting the likelihood term at early sampling steps. That is a very technical but very important point. AI here is not a black box that spits out a map. It is a probabilistic engine that must be carefully calibrated to avoid hallucinating structure that is not really in the sky. Everything about this field depends on simulations. AI does not learn dark matter from raw sky images in a vacuum. It learns from forward-modeled universes because the relationship between cosmology, baryonic physics, lensing geometry, and observed galaxy shapes is too complex to write down in one tidy equation. The weak lensing benchmark literature makes this explicit. Accurate analysis needs simulated data because the late-time density field is highly non-Gaussian, and standard analytic likelihoods become inadequate on the small scales where the interesting information lives. The challenge is that simulations themselves are imperfect. A 2026 weak lensing uncertainty benchmark says that real weak lensing analysis must handle realistic systematics and distribution shifts, because simulations are expensive and mismatches between simulated and observed data can bias cosmological inference. In its dataset, the authors include baryonic feedback, photometric redshift uncertainty, and shape noise, then require models to estimate cosmological parameters and detect out-of-distribution cases. That is a very honest picture of the field. The hardest part is not training a neural network, but making sure the neural network survives contact with reality. That is also why the community is moving toward benchmark challenges, standardized datasets, and uncertainty-aware models. The Fair Universe Weak Lensing Challenge was created specifically to compare methods under realistic systematics and distribution shifts, so researchers can test not only accuracy, but robustness. That is exactly what you want in cosmology, because a model that is slightly more accurate on clean simulations but brittle on real observations is worse than useless. It is dangerous. The reason this is accelerating now is that the next generation of surveys is enormous. Euclid will observe billions of galaxies over more than a third of the sky, while Roman is designed to map dark matter with weak lensing over a vast cosmic volume and much higher precision than before. ESA describes Euclid as a mission to explore the dark universe through large-scale structure, and NASA describes Roman as a mission that will map dark matter more precisely than ever before. The data volume is not just bigger, it is qualitatively different, wider, deeper, and richer in small-scale information than the older survey era. And here is the really striking part. AI is already being used operationally in the survey pipeline. ESA says Euclid's strong lens search used AI to pre-select about 300,000 images from 72 million galaxies in DR1, and scientists expect the data to reveal more than 10,000 new lenses. That is not a theoretical paper. That is real survey triage at astronomical scale. AI is helping decide where to look more closely, because humans cannot inspect tens of millions of galaxies one by one. This is why the future of dark matter mapping will not be AI instead of physics. It will be AI plus physics. Physics provides the structure of the forward model: gravity, lensing geometry, redshift dependence, baryonic feedback, and survey noise. AI provides the flexible inference engine that can learn from simulations, denoise observations, and capture the higher-order, non-Gaussian patterns that standard methods miss. The best systems will be the ones that preserve physical consistency while extracting every last bit of information hiding in the lensing field. So what is AI really doing here? It is taking a problem that used to look like a blurry statistical shadow of the universe and turning it into a reconstruction problem, where the goal is to infer the underlying matter field from noisy, incomplete, distorted observations. In weak lensing, the raw map is not the answer. It is only the clue. AI helps us turn that clue into a mass map, and the mass map is what lets us study how structure grew, how galaxies formed inside that structure, and whether our cosmological model is missing something fundamental. That is why mapping dark matter with AI matters so much. It is not just a technical upgrade, it is a new way of reading the universe. Every tiny shear in a distant galaxy is a fingerprint of invisible mass somewhere along the line of sight. AI does not create that information, it uncovers it. And as Euclid, Roman, and the next generation of surveys keep flooding us with sharper lensing data, the real question is no longer whether we can map dark matter. The question is how much of the cosmic web we can finally recover before the noise wins.